Hi guys, and welcome to another physics video, and in this video we're going to have a look at vector multiplication, and in particular the dot product and the cross product. Now, in the last video I introduced the concept of a vector, which has both a magnitude and a direction. We normally represent this vector by drawing out an arrow. So the length of the arrow normally represents the magnitude, and the direction of the arrow normally represents the direction. And a vector quantity is of course different to a scalar quantity. So we said that scalar quantities were things like energy or power or stuff like that. But vector quantities, they're a different type of mathematical object, and things like force and momentum and displacement, they're all vector quantities. And so we represent vector quantities by putting a little arrow over the top of vectors. Now, we also said that we could add vectors by adding the individual components of a vector. So we add the x components of a vector and our y components of a vector. So say we have two position vectors, r1, and r1 is 2x hat plus 3y hat. And we have another vector, r2, which is, let's call it 7x hat minus 4y hat. Then to add them together, we simply do r1 plus r2, and then we add the x components, so we're going to end up with 9x hat. And we add the y components, we're going to have plus 3 minus 4, which is just minus 1y hat, or minus y hat, don't need the 1 there. So it's pretty basic, you just add the components of a vector together. Now, another way I actually didn't mention in the last video of adding vectors together is actually to draw them tip to tail. And what I mean by that is by drawing one vector a little bit like that, and another vector like that. So we have two vectors. So say this is vector A and this is vector B. Now, the addition of this vector and this vector is exactly the same as if you'd have just drawn one vector going up like this. So what this is saying is that A plus B is just another vector, which we can call C, like that. So just A plus B equals C. So you add them tip to tail. You put the tail of the second vector next to the tip of the first vector. And of course, subtracting vectors is actually pretty similar. A good way to think of subtracting vectors is basically just adding the negatives. So say we want to do A minus B, then what we want to do is, instead of adding B, then we actually just flip the vector. So here's our A vector, I've drawn it over here for a good reason. Instead of subtracting B, we add the negative of B, and the negative of B is just like that. So it's the same length, but of course it's just the opposite direction, and that is minus B. So A minus B is just the same as A plus minus B. So that's a good way of thinking at it. And of course, we're going to get another vector, we can call it D or something, or use C. And so we can just say that D equals A minus B. But what about vector multiplication? Well, we said that if we multiply a vector by a scalar in the last video, so say we have a scalar quantity, just like the number 3, and we had a vector quantity, we had a vector, so say we have 2x hat plus 5y hat, then that's quite straightforward. We just simply multiply each component of the vector by the scalar. So it's just like expanding a bracket. We end up with 6x hat plus 15y hat. So generally we can say that a scalar A multiplied by a vector B is just another vector C. So scalar multiplied by a vector is a vector, and we just simply multiply each component in the vector by the scalar. But what about two vectors? How do you multiply two vectors together? Well, you may think, so say we have two vectors. You have vector A, we say is 4x hat plus 5y hat. And we have another vector B, which is 6x hat plus 3y hat. You might just think, why don't we just multiply each component together? And so you will say that A multiplied by B is just, well, what would it be? 24x hat plus 15y hat. But that is not the case. That is not how we multiply vectors. Unfortunately, it is a little bit more complicated than that. And instead of doing that, there are actually two different operations: the dot product, or the scalar product, and the cross product, or vector product. And we're going to talk through each one of those step by step. Now, formally, the dot product between two vectors is simply the projection of A onto B. It's basically how much of A is in the same direction of B multiplied by the length of B. And the important thing about the dot product is the result is a scalar. So the dot product always produces a scalar. Now for the other one, the cross product, the magnitude of the cross product of two vectors A and B is the area of the parallelogram that is spanned by the two vectors A and B. Now the result of the cross product is actually a vector, and it's only the magnitude of the vector represents the area. And the direction of the resulting vector is perpendicular to the plane containing the parallelogram. Now we'll go through all that in a little bit more detail in just a sec, but let's start out with the dot product. So let's say we have two vectors. We have vector A and we have vector B. So we want to find the dot product of two vectors. Well, the dot product of two vectors, the way to actually calculate it is we can say that the A dotted with B, this little dot notation, this means we're taking the dot product between vector A and vector B, is one and the same as the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between A and B. And that angle we're going to call theta. So this kind of makes a bit of sense. It's if A and B are pointing in the same direction, then you're going to get a higher dot product than if A and B are pointing at right angles. And it turns out that if they're actually pointing in right angles, you're going to get 0 for the dot product between A and B, because of course cosine of 90 degrees is just simply 0. And the other thing to note about the dot product is that A dotted with B is one and the same as B dotted with A. And in the last video we said that that was called commutative. So it doesn't matter which way around you multiply them, you'll still get the same result. So as I said, let's take the case in which A and B are perpendicular to one another. So we have A and B. Then, and this angle right here is 90 degrees, or if you like, pi over 2 radians. And how do we calculate the dot product? Well, we know that it's the A dotted with B is the magnitude of A multiplied by the magnitude of B multiplied by the cosine of theta. Now, we don't know what A and B are, but we do know that these two vectors are at right angles. So we can simply say that A dot B is AB cos of 90 degrees, or pi over 2 radians, and cos of 90 degrees is just 0. So the dot product between two vectors that are perpendicular is 0. These vectors there's no projection of A onto B because they're at right angles. So how do we actually work out the dot product if we're given two vectors, if we know what the vectors are? Well, we actually have to multiply the components and then add those products together. And I'll show you exactly how to do that with an example. So let's say we have two vectors, and the first vector A is 3x hat plus 4y hat. And we have another vector b, which is 6x hat minus 2y hat. Now to work out the dot product, we have to multiply both of the x components and then add that to the product of the y components. So a dot b is one and the same as 3x hat plus 4y hat dotted with 6x hat minus 2y hat. And this, well, let's multiply the x components. We're going to get 18 for the x, and we're going to add that to, well, 4 times minus 2 is minus 8, and that just simply gives 10. And so you can see that the result is just a number, it's just a scalar. All the vector stuff has gone. And so that is how to calculate the dot product. Now, what happens when we try and dot a vector with itself? Well, let's just try it. Let's just try dotting the vector A with itself. Well, what's that going to be? That's going to be 3x hat plus 4y hat dotted with 3x hat plus 4y hat. So what's going to happen? We're going to end up with 9 plus 16 right around here. And that's going to give 25. But of course, that is just the square of the magnitude of the vector A itself. If we work out the magnitude of A, we simply get that it is the square root of 3 squared plus 4 squared. This is quite a well-known Pythagorean triple right here, which is of course the square root of 16 plus 9, which is the square root of 25, which is 5. So we can see that the dot product with a vector as itself is just its magnitude but squared. So more formally we can say that A, the magnitude of the vector, is simply the square root of the dot product of the vector with itself. Now what I want to do is have a look at unit vectors. Now unit vectors have one job, and their one job is to point in a particular direction of the axis. And their key thing is that they always have a magnitude of 1. So we actually said in the last video that the x hat vector and the y hat vectors are unit vectors. They both have a magnitude of 1. But actually it turns out that we can create any unit vector in a certain direction. It doesn't have to be just these boring old ones here. We can actually create any unit vector. But the one condition is that the unit vector has a magnitude of 1. So let's see if we can create a unit vector that points in the direction of A, but of course has a magnitude of 1. Well, with any unit vector, we normally give it the little hat, and this basically denotes that it's a unit vector. You don't have to worry about the arrow. The hat will tell you that it's a vector that has a magnitude of 1. And the way to do that is you divide the vector itself by its magnitude. So you simply do A over the magnitude of A. And what are we going to end up with? Well, we said that A is 3x hat plus 4y hat. And what was the magnitude of A? Well, we worked that out just a second ago. It was 5. So we can say that the unit vector pointing in the direction of A is 3/5 x hat plus 4/5 y hat. And if you work out the magnitude by taking the square, adding the squares together and square rooting it, you'll simply end up with 1. So this vector right here points in the direction of A. So that wraps up the dot product. So now let's have a look at the cross product. Now we say that the cross product of two vector is written as C, which is a vector. I said that the cross product always, and you ended up with a vector as opposed to the dot product, you ended up with a scalar. You always ended up with a vector if you take the cross product of two vectors. Then we can say that C is A cross with B. And that little sign there means that you're taking the cross of two vectors. And of course, the result is a vector. Now, the magnitude of the vector C is given by, well, it's the magnitude of A crossed with B, but it is the same as the magnitude of A multiplied by the magnitude of B multiplied by the sine. This time it's the sine of the angle between A and B. So if you actually draw it out, then you'll have vector A, vector B. Now you have to imagine that vectors A and B all lie in this plane. So there is a flat plane that vectors A and B all both lie in. So here's vector A, here's vector B, and they're lying in this plane. And C, the cross product vector of A and B, points perpendicularly to the plane that both of them are lying in. So this vector right here, you have to kind of imagine it's 3D. It points in the direction that's perpendicular to both vectors. It's perpendicular to the plane that both vectors are in. So if you imagine the plane was just this sheet of paper, the cross product would actually point upwards. It would point out of the plane of the diagram. Now this cross right here is actually quite a complicated little operation. And to see what it does, let's do an example of how of calculating the cross product. So let's say we have two vectors. I'm going to take two quite simple vectors right here. So let's say we have vector A is 2x hat. It only has an x hat component. It doesn't have a y hat component. You could alternatively think of it as 2x hat plus 0 y hat plus 0 z hat. We're actually going to need the third dimension here for a reason you'll just see in a moment. And B, we're gonna call B 0x hat. It's not going to have anything pointing in the x hat, but it's going to have 3 y hat right there. So, and it's not going to have a z hat component. So, you know, I've written out some unnecessary stuff. A is just 2x hat and B is just 3 y hat. Let's try and cross these two vectors here. How do we do it? Well, we can write the cross product of two vectors in the form of a matrix determinant. And what do I mean by that? Well, I mean that A crossed with B is the determinant of the matrix that is formed by taking the x hat unit vector, y hat unit vector, and z hat unit vector. So we always put these three unit vectors on the top row, and in the second row right here of this matrix that we're defining, again, we'll see why this is the case in a minute. It's a bit counterintuitive, but we'll have a look in a moment. So we've got the x component of A, the y component of A, the z component of A, and the x component of B, the y component of B, and the z component of B. So we've just formed a matrix out of the 3 unit vectors, the 3 components of A, and the 3 components of B. Now, this is the general form of how to work out the cross product between two vectors. For this specific case, what are we going to do? Well, we're going to write out our unit vectors right here, x hat, y hat, and z hat. And we're going to substitute in the components of A. So it has 2 in the x hat, but of course the others are just 0. It doesn't have anything in the y hat or the z hat. And for the vector B, we're going to put a 0 here because there's no x hat. And it's got 3 in the y hat right up here. And it's got nothing in the z hat. Now, you might already know how to work out the determinant of this matrix right around here. But if you don't, I'll show you how to work it out. It's a bit tedious, but I'll talk you through each step of the way. And again, it's a bit counterintuitive, this, but let's just roll with it for now. So, to work out the determinant of a 3x3 matrix, you have to take this element of the matrix right here, which is x hat, and you have to multiply it by the determinant that is formed by all of the elements that are not in either the same row or the same column. So I've got another pen here, which is quite handy. So if you delete So this is the element we've got. If you get rid of if you hide all of the components that are not in the same row or the same column, you end up with a 2 by 2 matrix right here. So it's 0, 0, 3, 0. And that is what we have to take the determinant of. So we have to now take the determinant of this 2 by 2 matrix. Now you actually have to subtract the next one away when evaluating the determinant. So you subtract y hat, and now what we're going to do is we're going to hide all of the elements that are not in the same row or the same column. And you can see we've got another determinant formed. We've got two matrix formed. We've got 2, 0, 0, 0. So that's another mini determinant right here. So 2, 0, 0, 0. And we plus the next one, z hat, and then what's the one that's going to be missing? Well, let's delete all of the elements that are in the same row and the same column. 2, 0, 0, 3. So that is our z component of this. So we've got 2, 0, 0, 3. Now, for completeness, I will just write out which elements you add and which elements you subtract. You basically subtract all of the elements that are in these corners, and then you add all of these. So it's a bit like a weird kind of checkerboard almost. So as you saw then, we added the x, we added the z because they were in that position there and that position there, but of course we subtracted the y because it was in that position there. I don't know why, but it's just what we do. It's just what works, and so you can't really argue, I suppose. So let's evaluate this right here. So to work out the determinant of a 2 by 2 matrix, we simply do that times that minus that times that. And what's that just going to be? That's just going to be 0. So A cross B is going to have nothing in the x hat direction. So it's going to have 0 x hat. And actually similarly for the y hat direction, well, we're going to have 2 times 0 is 0, minus 0 times 0, just 0. So it's just going to get a lot of zeros. And so we're going to have nothing in the y hat. But what about the z hat? This looks a bit more promising. We've got 2 times 3, which is 6, minus 0 times 0, which is 0. So what does that leave us with? That leaves us with 6 z hat. And so we find that the cross product of A and B, remember we said that A was 2x hat and B was 3y hat. The cross product is 6z hat. Now, what can we notice about this result? Well, we can see that the resulting vector here, 6z hat, is perpendicular to both vector A and vector B. See, vector A was pointing entirely in the x hat direction, vector B was pointing entirely in the y hat direction, and the cross product just points entirely in the z hat component. And you also notice that 2 times 3 is essentially 6. So let's draw it out. So let's draw out what we've just done. So let's draw vector A. That's 2 in the x hat direction. We're gonna say that they're gonna define our axes right here. This is the x direction. This is the y direction. This is the z direction. So that's just our axis reference. And so we've got this vector here is 2x hat, and this vector is 3y hat. And I'm not going to draw this to scale, but the cross product is 6z hat. And so we know that since they're all aligned with the axes, all these vectors, that all three vectors are perpendicular to one another. And since they're perpendicular to one another, this is actually a rectangle. This is a straight-sided rectangle. Those two sides are parallel to each other. Those two sides are parallel to each other, because you've got to imagine this is all on a plane right here. I know I've drawn it like a parallelogram or a rhombus, but this is actually a rectangle in 3 dimensions. And so we can see that the magnitude of the cross product, which is 6, is the area of these two vectors. So 2 times 3 is 6. Whereas if we were to have two vectors that weren't that weren't right angles to another, so this time this angle is theta, it's not 90 degrees, then this would form a parallelogram right here. So these two vectors would span out a parallelogram, and the area of a parallelogram is given by AB multiplied by the sine of theta. And we can see that if theta is 0 degrees, then we're not going to get any area at all, and so we're just going to get 0 as the cross product. And that basically says that if you cross two vectors that are pointing in the same direction, you're going to get 0. So this basically says that A crossed with A, so if you cross two vectors that are the same, you're going to end up with 0, because it's not going to span any area. It's like, having my two arms right here, they're parallel, they're not spanning any area. Whereas if I open them up to 90 degrees, then I'm going to have maximum area. There you go, that's probably a bit better. So no area, and then maximum area right there. It's also worth noting that the cross product between two vectors is what's known as anti-commutative. Now, I said the dot product was commutative, and that said that A dot B is B dot A. We said that a few minutes ago. But the cross product is what's known as anti-commutative, and that is basically saying that A crossed with B is one and the same as minus B crossed with A. So if I was to do 3y hat cross 2x hat, I would actually end up with minus 6z hat. It would be the other way around. Now, you might be able to see a bit of a problem with the cross product, because how do we know which way round the actual result is? Because it could technically be either that way or that way. We've kind of chosen a little bit arbitrarily, like that it's going to be that way. But you might think, well, why is, if you've got the x-axis there, if this is the x-axis, this is the y-axis, just as before, why are we setting the positive z-axis upwards? I mean, it could just as equally be downwards. And you're perfectly right. It's arbitrary that we've chosen this choice, but this choice right here, this is what we know as the right-hand system. This is a right-hand rule. And basically how it works is if you take your right hand and you curl your fingers from A to B, then your thumb will always point in the direction of the cross product between A and B. So let's see if I can try and do this. See if you can see that if I curl this in the direction of this, I'm going to get that. And as you can see that the cross product points upwards. So it's just like in the diagram. And this is a right-hand system. It's what's known as the right-hand rule. And I'll draw it out for you. You basically have, if you have two vectors right here, this is vector A, this is vector B, then we go around in this direction here. It's the same direction as my fingers. You're curling it in the direction of B, you're going from A to B, then the cross product will point that way. Not the magnitude, it's just the cross product points in that direction. It's perpendicular to both, but it points that way. And finally, let's have a look at an example question. So we have the vector A, which is equal to 3y hat plus 4z hat, and the vector B, which is 2x hat minus 2y hat. And our job is to find C, which is the cross product between A and B. So how are we going to do this? Well, we're going to draw out our mighty determinant right here, our mighty matrix determinant. We're going to draw the three unit vectors right here, x hat, y hat, and z hat. And we're going to input vector A, nothing in the x hat, it's got 3 in the y hat and 4 in the z hat. And B, we've got 2 in the x hat and a minus 2 in the y hat and nothing in the x hat. So let's do our long-winded, arduous determinant evaluation. So what are we going to end up with? We're going to have x hat multiplied by the determinant formed by the 2 by 2 matrix that is formed by deleting all the elements in the same row and the same column. Basically, I think it's just helpful to, use a pen to hide them, and then you can clearly see what you're doing. So 3, 4, minus 2, 0. 3, 4, minus 2, 0. So that's our first mini one. Minus y hat. And what's the mini matrix, the mini determinant that's going to get formed by crossing out all them? 0, 4, 2, 0. 0, 4, 2, 0. Plus z hat. And what are we going to get? You're going to get 0, 3, 2, minus 2. So 0, 3, 2, minus 2. So let's go ahead and evaluate all these determinants. Well, 3 times 0 is 0. Minus 4 times minus 2. Well, we've got 0 minus 8, which is 8x hat. So see the 2 minus signs careful. You've got to be pretty careful when evaluating these because it's very easy to make a mistake. And what are we going to get in the y hat? Well, we're going to get 0 times 0 minus 4 times 2. Now this would be minus 8y hat, but of course there's another minus sign here to cancel that. So you're going to get 8 in the y hat direction plus 8 in the y hat direction because we've got minus 8 here, cancelling with this minus here. That's going to give us plus 8. And what about the z hat? Well, 0 times minus 2 is 0, minus 6, and that's not going to cancel. That's plus minus 6 z hat, so that's going to be minus 6 in the z hat direction, and that is the cross product between A and B. And the next thing we want to do is we want to find the angle between A and B. Well, we said before that the magnitude of C, the magnitude of the cross product, is equal to AB sine theta. And so if we rearrange this equation right here, we find that sine of theta is the magnitude of the cross product divided by the magnitude of the vector A and the magnitude of the vector B. I'm using a bit of dodgy notation, I've just realized. I'll make it a bit more clear that the magnitude of the vector A is one and the same as A without any arrow. So this is a scalar. The magnitude of the vector is just a scalar, and for completeness, I'll just write out B. So the magnitude of B is just B. So I've done a bit of a notation change there. So what's the magnitude of C? Well, that's going to be the square root of 8 squared plus 8 squared plus minus 6 squared. Typically, when you're evaluating magnitudes, you don't actually have to worry about any of these minus signs because, of course, any minus sign squared just goes to positive. So you might as well just write 8 squared plus 6 squared. So you can just kind of ignore the minus sign, which is quite nice. And you divide that by the magnitude of A, which is 3 squared plus 4 squared, multiplied by, that's not a cross product, that's just multiplying, 2 squared plus minus 2 squared. And now it's just a question of evaluating it. And if you evaluate all that on your calculator, you'll find that the sine of the angle between A and B equals 0.906. And that's, of course, sine theta. You need to make sure to take the arc sine of both sides. So theta is arc sine of 0.906. Sorry, I'm just not on screen quite, is it? 0.906, and that is, depending on whether you're in degrees or radians, that is just 64.9 degrees, around about that, or in radians, that is 1.13 radians. So that's how you work out the angle between two vectors. If you know the cross product, then you can just rearrange for sine theta and then arc sine it right at the end. So that concludes vector multiplication. And I hope that helps, and I'll see you in the next video.